everybody, welcome back to 113. Give me just a quick yes if the audio seems okay for the mic, no if something's wrong. And I can always fix it up. Generally seems okay. Okay, cool. Sounds good. Well, welcome back to Studio Winston. It got its name today. Let me stop sharing my screen here. Switch over to our notes page. Actually, let's just stop sharing altogether. Because Studio Winston gets its name, get this off here, from Winston. That's Winston. Say hi, Winston. Yeah, that's Winston. So Winston's with us in the studio today. Hopefully he won't fall asleep. He usually just likes to fall asleep sitting next to me. Okay, now we can go ahead and share. Turn off the sound over there. Move this over here. So our goal for today is go over a couple more examples of our CSTRs. If we get far enough into our examples, we'll be able to see a couple of different iterations of the same example and then how to solve that same example inside of MATLAB. In fact, I might cut the middle part of the example just to make sure that we have enough time to solve it in MATLAB, because the structure that we'll go over is very similar for all of the problems in MATLAB. So it's good to see that once. And then in the second portion of the lecture, the one from 3 to 350, we'll introduce the energy balance. So if we don't get to quite everything in the first 50 minutes, we'll still have our FICA from about 245, 250 up to 3. If we have to finish up some of our example there in the second lecture, we'll do so, but we'll definitely be able to get to the energy balance for this one. So I'm going to move my windows around just so that I can see you if anybody texts or sends a message in chat along the way. Oh yeah, he's sacked out. He's also leaning up against my arm, so hopefully my arm doesn't fall asleep. There's an interesting question. So every once in a while, a student will come to me and say, you know, I want to work in field X with a chemical engineering degree. Like, can I get a job there? My answer is usually like, yes, with an asterisk, you can probably get a job there. It just depends on exactly what you want to do in that particular field. Are you uncomfortable? So let's say, for example, I want to get a job at Tesla as a chemical engineer. What can I do at Tesla as a chemical engineer? In their battery manufacturing process at Tesla, they have to use all sorts of different chemicals as solvents and whatnot for their batteries. And so you may be involved with a solvent process in the battery manufacturing. Oh, he's done. Winston's going to leave us. It's not going to be Studio Winston. He's very upset. Say goodbye, Winston. Okay, bye-bye. So, you know, you could work at Tesla as part of their battery manufacturing process, but not really as anything that's outside of chemical engineering experience, because so many of the processes involved in assembling a battery look like traditional chemical engineering. So for example, some of the solvents that they might need, there's one called NMP, which is, I can't even pronounce all the letters from it or all of the words from it. There's another solvent that's very commonly used in batteries, which is called xylene. You may have also found xylene, oh, let me make sure my pen's working. So xylene is a very common solvent. It's very good at dissolving organic chemicals, and there tend to be a lot of organic chemicals in a lot of different manufacturing processes. Xylene comes in a number of different forms. The most common form that you get is actually a mixture of 3 or 4 different forms of xylene. Actually, it's a mixture of 3 forms of xylene, and it comes usually in a lot of paint thinners. So if you've ever worked with any kind of like an oil paint or any kind of an oil-based paint, and had to use a paint remover with it or a paint thinner, that smell that you have smelled was probably a xylene smell that you had. And the 2 that we're interested in right now are, well, I should say, this is the general form of xylene. So it looks like a benzene ring. and then it's got a CH3 group up at the top. And then depending on where the other CH3 group is, we call these things different types of xylene. So if there's a CH3 group here, we call this orthoxylene, and that's abbreviated as O. That can form what we call an isomer with a different type of xylene. So other types of xylene have the same CH3 group up at the top, and then there's another CH3 group on one of the sides. And so the other version that we're interested in today has the CH3 group over here, and this is called metaxylene. There's a third one called paraxylene. We're just not interested in that today. And this sort of a reaction that we're dealing with here is called an isomerization. The reason it's called isomerization is because ortho and meta and para are what are called isomers of xylene. And so this example that we're going to be looking at is xylene production. So, you know, if you ask, well, where could I go and work at Tesla or at a battery company or something like that with a chemical engineering degree? Yeah, you could be working at different points in that company. One potential option is that you could be on either, say, the manufacturing or the purification or the recovery of a solvent stream, because those can be extremely expensive to buy. So the example that we're going to look at has to do with xylene. I don't have any inside information about Tesla, so it's not like I can tell you how they would specifically use xylene over at Tesla other than the general battery solvent kind of thing. We would have our typical CSTR that we're pretty much always going to draw as a box because that's what it's going to look like for us. And so the feed that we have going into our CSTR, actually, let's write our reaction over here. So we're going to call orthoxylene A, and we're going to call metaxylene B. It's usually just faster to abbreviate things as A and B. There's no reason for it. Sure, I can scroll up a little bit. And so our general reaction will be the reversible reaction of A goes to B. And it's all going to be liquid phase. So our first few examples until we get partway through next week, everything up until next week is going to be liquids. And we will get to gases later because we require a little bit of extra work for gases. So we've got this reaction A goes to B, and we know that its rate constant is 0.06 per hour. And that is specifically at 60 degrees C. So this is the type of information that's very often provided to you at the beginning of a problem statement, is things like, what's the reaction? What's the rate constant at a particular temperature? Maybe they tell us the activation energy. In this case, I think I said it was 25 kilojoules per mole. And then they tell us a little bit about what's being fed into the system. So the inlet concentration, it's going to be pure xylene, specifically pure A, right? So this is, remember, pure A is the orthoxylene that we've got. So it's pure A. The concentration, because it is pure, this is kind of a neat thing if you're ever worried about getting a concentration and you don't know what it is. If you know it's pure and it's like a real substance, if I'm telling you orthoxylene, because that's a real thing, inlet concentrations can always be estimated as the density divided by the molar mass. So if you can look what is the concentration of pure water, and you can write the molar concentration. So it's a real thing. It's not like we just make these numbers up. It's just density divided by molar mass. Usually we don't need that kind of an equation, but every once in a while we do. If we were to plug in the numbers for pure orthoxylene, what we would end up finding is that this is 8.5 moles per liter. So if I just have a jar of orthoxylene sitting around, it would have a molar concentration of 8.5 moles per liter. And then it's being fed at a rate of 1 liter per minute. The reason, by the way, that we often choose concentrations and volumetric flow rates is a very practical one. we have ways to both measure and control these variables. It's very rare that there's any kind of an instrumentation that you could put onto a stream that would tell you what's the moles coming out. We have ways of getting concentration and ways of getting volumetric flow rate very easily. And so we're often in a situation where we have to start with those as our measured variables. What does the P stand for? Oh, sorry, this is not supposed to be a P. It's supposed to be a density, which is a rho. Let me edit that. That's the Greek letter rho, which is density. So something like, water would be 1,000 kilograms per cubic meter, something like that. Thank you for pointing that out. Our reactor volume that we're initially going to deal with is 0.2 cubic meters. I hope the trash man isn't too noisy. They're picking up my trash outside right now. So we've got a reactor volume of 0.2 cubic meters. And we've got a couple of parts to this question. As you may have noticed in the homework, it's like that engineering meme. Yeah, there's only like 4 or 5 questions, and then each one has like 6 subparts to it. So the first part of this question is, what's the conversion of A? So orthoxylene. Oh, I forgot to mention the temperature in our reactor is 90 degrees C. It's another piece of information. We were given that particular piece of information. Once we find out the conversion of A, very common kind of question that we would be asked, given a particular size, what's the conversion? Another question that we can ask is, what volume is needed to get 90% of the equilibrium conversion? Yeah, K, we're going to end up having to change K. There's a question in chat, will K end up changing? Yep, because our reactor is at one temperature and the K that we were given is at a different temperature. And then the last problem that we'll get to, and this is the part that might go into the next part of the lecture, solve number 1 in MATLAB. Right, so 3 different parts to this question. The first question is sort of take everything as it's given, find out what the conversion of A is. And then the second part says, well, what if we could make that reactor volume anything we wanted it to be in order to get up to 90% of equilibrium conversion? And we're going to spend a little bit of time talking about what this phrase means, which is a percentage of equilibrium conversion. It's just a little bit of jargon that you'll have to get used to, but it's pretty easy to apply in our system. And then the third one is basically going to serve as a check to our first problem. We're just going to solve exactly the same thing, except instead of doing it by hand, we're going to do it in MATLAB. The reason being, when we do it in MATLAB, the setup is a little bit different. Not that it needs to be, but I'm going to set it up a little bit differently so that you have the tools that you need, for example, for multi-reaction problems. All right, so let's take a look at part 1. So part 1, we're just saying, what is the conversion of A? If you notice in your book, the very first thing that I start with is always the overall material balance, because you can usually get started very accurately if you always start off with the overall material balance, on the species material balance, which in this case is just for A. We can write another one for B if we wanted to, but at the moment, we don't think we need it. So this is the material balance for A. If we wanted to write the material balance for B, it'd be exactly the same thing, just switch all the subscripts from A to B. And so now the way that we're going to go about this is as follows. We're going to look from left to right. We're going to write all of these as functions of n sub A. So we're not going to know what's coming out the other side, right? N sub A right now is unknown. We don't know what the conversion of A is, but we know that if we could figure out how much is coming out the other side, then we could probably figure out what the conversion is. So if we have to write each one of these terms as N sub A, we don't have to work very hard on this one, right? The very first term is n sub a. I don't have to rewrite that as a function of n sub a because it's already a function of n sub a. We'll say write as a function of n sub a or a constant. All right, so we can have numbers and stuff too. Numbers and stuff are okay. So now let's look at n sub a 0. The 0 also over here on the left-hand side. It's good to go, right? We're okay if it's a number. We're just trying to get down to variables. So now let's look at n sub a 0. Generally speaking, n sub a 0 is going to be equal to c sub a 0 times v0, right? That's our definition. That there's no guessing or assumptions that have to go into that. That's just the way that this is defined. So our c sub a 0 was 8.5 moles per liter. And our inlet volumetric flow rate was 1 liter per minute. So we're left with 8.5 moles per minute. You definitely want to get into the habit of tracking these units around, especially when you see units of time. Units of time and units of energy tend to be the ones that get mismatched most often. Usually the moles and stuff like that, I don't know, that just tends not to be a problem that often. It's just people remember the moles. But if rate laws are given in minutes or seconds or hours or whatever, and flow rates are given in something else, it's very easy to forget that those have to work out, right? They have to be the same set of units because the material balance has to be dimensionally consistent. So now we're good to go with n sub a 0, right? This is just a number. So we're good with n sub a 0. We're just going to write that in as a number. We're now left with the last one. We're not really worried about V. V is just a number. It's 0.2 cubic meters. The one that often takes the longest is R sub A. Usually we have to do the most amount of work on the rate law in order to get it as a function of whatever it is we're trying to solve for. So in this case, N sub A. So let's work on that one. The rate of A, if you think back to the general definitions that we had in the discussion of rate laws that we went over previously, the ones that John brought up, it's the stoichiometric coefficient of A times the rate of reaction. So the stoichiometric coefficient of A is -1. How do I know it's -1? Because I wrote the reaction that way, right? So this is an example of we were essentially given this reaction. I can solve the whole problem if I went back through and put a 2 in front of everything, if I just doubled all the stoichiometric coefficients. That would be okay, except we were given the rate in this, or given the reaction in this particular form, and the units of the rate here are consistent with an elementary rate law written for that particular reaction. So this is why, yeah, technically you could change stoichiometry if you wanted to, but it would become a mess, right? Because you'd have to try to keep track of, well, the rate was written for a different stoichiometry than the one that I was given, and for whatever reason I chose to change it. So this is a great example of if you're given a rate law and a reaction, just use it the way that it's written. Don't try to change any of the stoichiometry. Technically you can, but it's very hard to keep track of all of the changes. So with a reversible rate, the general R, this one here, will be equal to the rate constant K times the concentration of A minus the concentration of B divided by our capital K sub C. I'm going to put the little caps on the K sub C to remind you that that's uppercase, because this one is our equilibrium constant. And this K is our rate constant. So our rate constant is supposed to be lowercase and our equilibrium constant is supposed to be uppercase. This form that I just wrote, the KCA minus CB over KC, that's sort of the shortcut form that John was talking about when he did his reversible reactions coverage. And you can always write the forward minus the reverse and end up with exactly the same expression. Eventually you would need to get it down to here anyway. So if you don't remember where that one came from, we'll review chapter 3. There's a question in that chat. I thought Kc is equal to Kf over Kr. That's the way that it's defined, and then it happens to be equal to the way that we've used it here. Kc is equal to a lot of different things, unfortunately, or maybe fortunately. That makes it a very powerful tool. So we've done a little bit of work here, but now we need to try to express each one of these values in terms of either a constant or n sub a. So the rate constant K has to be the rate constant K at the temperature of the reactor. And so the temperature of our reactor is 90 degrees C, but we were given K at 60 degrees C. So K at 90 degrees C is equal to K at 60 degrees C times the exponential of E sub A over R, 1 over T sub R minus 1 over T. Let's get my parenthesis here. And so we've got two T's to deal with inside of there. The K of 60 degrees C, that's the one that was given to us as 0.06 per hour. The T sub R is the temperature at which that was given, which I just wrote there a moment ago, was 60 degrees C. But this expression always requires absolute temperatures. So we're going to adjust that to Kelvin by adding 273. This temperature is the temperature of our reactor. And so this is going to be 90 plus 273. There's a good sort of rule of thumb that you can try to keep in mind whenever you're adjusting a rate constant for K. The behavior of rate constants in response to temperature changes is always the same. If the temperature goes up, little k also has to go up. So if you're ever worried about getting these two temperatures reversed, try it one way. If the temperature went up and the K went down, you did it wrong. Just flip the two around. If you did it correctly and the temperature went up, then K will also go up. So for example, if I plug in all of these values, the K that we need, which is the K of 90 degrees C, if we calculate each one of those, will end up being 0.006. And I did a unit conversion here. This is why I said earlier that the unit conversions are worth mentioning. It's per minute, right? I went from per hour to per minute. The reason that I went to per minute is because I want these time units here to match the same time units that I've got everywhere else. I've already started to use minutes up here. And so I converted from hours to minutes to be consistent with everything. You could have done it the other way around, right? You could have said, well, I want to use units of hours everywhere and converted all of your flow rates over to hours instead of the rates into minutes. As long as you're consistent with your units, they would be okay in both of them. But I chose to use minutes here just because it seems like there were more minutes floating around than there were hours. How's this approach different than using R is equal to KCA in the last lecture? That's a good question. It's worth a little aside here. In the previous lecture, we had A goes to B, and so we would write R is equal to K times CA. This is because that reaction was irreversible. Right, so the key difference between last lecture and this lecture is the reversibility of the lecture. I don't think I converted it wrong. It's just I also applied the exponential. So I did the entire calculation. Not that it's impossible. Double check my math, but I think I did that one right. The reason I think I did it right is because I also did it in MATLAB and got the same answer. But I could have done the same thing wrong twice. That is never beyond my capabilities to do the wrong thing twice. Don't feel bad if you do the wrong thing twice. That happens to everybody. So that's one of our constants. Let's knock out the other constant real quick since we're talking about constants. We also need the equilibrium constant Kc, and we need that at 90 degrees C. So in order to get the equilibrium constant Kc at 90 degrees C, we need a relationship between Kc and the other equilibrium constant, which is K sub A. And so K sub A, that's a really nasty K sub A. Let's see if I can clean up my K sub A. K sub A, that's a little bit better, at 90 degrees C. But it's K sub A at 90 degrees C times C sub T to the delta. How did I know that that's what that was? This was the summary table that John went over, which is table 3.1. So anytime you need to relate any Kc to Ka, go check out table 3.1. It shows all three of the variations that we would ever need. And so this is the one that we've got. So the math that there's a couple of people here. 0.06 divided by 60 is not 0.006, but the reason that I got 0.006 is because I already applied this. So check out table 3.1 each time that you need to convert from a KC over to a KA, we can pretty rarely calculate KC directly unless it happened to be given to us already. The delta term that's up here in the numerator is just one of those things that you have to remember. It's just the sum of the stoichiometric coefficients, which in our case is -1 plus 1, which is 0. And so the Kc at 90 degrees C just happens to be equal to Ka at 90 degrees C. So the way to go about getting K sub A at 90 degrees C is to do exactly what we've done in the last few homeworks, which is use the shortcut Ka equation. Hang on just a second. I got new headphones. They're a little bit itchy sometimes. So this particular Ka that we've got can be calculated from, or sorry, this Kc can be calculated from our shortcut K. So let's just continue it over here. K sub C is equal to K0, K1. Remember, these are all capital Ks because they're equilibrium constants. And so now I would have to go look up the enthalpies and the Gibbs energies of formation for orthoxylene and paraxylene in their liquid phase. Make sure you don't take the gas phase ones. They have to be in the liquid phase because our reactor is operating in the liquid phase. And if I were to calculate those, I would end up with 3.67. How do you solve for CT if delta was non-zero? If delta is non-zero, you better bust out the MATLAB because our C sub t is a function of CA and CB, and CA and CB are functions of NA, and we don't know what NA is. And so it becomes a big nonlinear problem. That's why a lot of the examples that you see are things like A goes to B or A plus B goes to C plus D or something like that. Okay, so there's our KC. Let's go ahead and knock out some of the things that we've got. So we definitely know -1, not a problem. We know K. We just found K sub C, but we're still left with CA and CB. So we have to either write those as numbers or write them as functions of N sub A. In order to do that, we use the definitions of C sub A. Why are we finding K0, K1 if Kc is equal to Ka times Ct times the delta? The reason we want Kc is because this value of Kc is, it was calculated by using K sub A, but this value of Kc goes into our rate law, right? This is the Kc that we need. Hang on just a second. Sorry, had a little dry spot there in my throat. Right, so the last thing that we need then are CA and CB. And we need them, again, either as numbers or we need them as functions. So C sub A is defined as N sub A over V. That's lowercase v for the outlet volumetric flow rate, but because it's a liquid, we can write N sub A over V0, right? So this is, until we get later into next week, this equality going from V to V0, this is for liquids. Because for liquids, we always have that the inlet volumetric flow rate is equal to the outlet volumetric flow rate. And that'll always hold for liquids. So this ends up looking like N sub A over 1 liter per minute, which is effectively just N sub A, right? The unit is there. It's a mole per minute, but it's been divided by a 1 liter per minute there. Similarly, C sub B, we start off with its definition, which is N sub B over V. Because it's a liquid, we can write it as N sub B over V0. And then from stoichiometry, we know however much A reacted is equal to the amount of B that we had here. So this step going from N sub B over to Na0 minus N sub A, this is like using your stoich table, right? Stoichiometry still holds. And if you were to write out the stoichiometric table for this, you would find out that n sub b is equal to n sub a 0 minus n sub a, which is convenient because we know all of those except for n sub a, right? So if I'm looking at this one, the n sub a for c sub a was fine, right? We're trying to write it in terms of n sub a. Here it's okay because the n sub a shows up. V0 is okay because it is 1 liter per minute. And n sub a 0 is okay because that's a number, right? That's 8.5 moles per minute. So we're now in a position where we can actually calculate the rate. So R sub A would be equal to 0.006, that's our K, in units of inverse minutes. Our C sub A is N sub A over 1, and then we're going to subtract off C sub B, and C sub B is NA0 minus NA divided by V0, and then that gets multiplied by our K sub C. Right, so this version that I just wrote here for R sub A, that is exactly the same R sub A that I wrote up here. I don't know if I can draw a long enough line to connect those two, but that R sub A, there we go, is the same as this R sub A, right? All I've done is substitute in the numbers for it so that we can then write that R sub A is 0.0139 minus 0.0076 N sub A. Oh yeah, sorry, there is a negative sign right here. Thank you. Forgot that. I left off that negative sign, but this one is okay. I have the correct version on the other side. So now we substitute all of that back into the material balance. Right, remember that our material balance was this, R sub AV. If we substitute those numbers inside of there, we'll have N sub A minus 8.5 minus our R sub A, which is 0.0139 minus 0.0076 N sub A times V. We have to be careful with our V here, right? Because remember our V was given as 0.2 cubic meters, but all of our concentrations are in terms of liters. So we have to multiply that by 1,000 to get 200 liters here. That was given in the problem statement too. So all of this times 200 in order to get liters. And what we see is we've got one equation with one unknown, right? We've got an NA here and an NA here. Everything else is a number. And so we can solve that expression. For NA is going to be equal to 4.7 moles per minute. The question, though, asked us for what's the conversion of A. So we just use the regular old definition of conversion that we've used previously, which is in minus out over in. And so this ends up being 1 minus 4.7 divided by 8.5, which is what, like 45%, 44.7%. Let's write that out twice, because I know sometimes, what do you mean by a percentage comes up, and that's this 44.7%, right? And so that's what the question was actually asking us was, what's the conversion of xylene at 90 degrees C? It's 44.7%. So the way that we got that was these three steps, right? We always start here, start with the material balance, then we do some substitutions so that we get to this expression, and then we solve. Right? It's usually those substitutions in going from part 1 to part 2 here, or from step 1 to step 2. Those substitutions are what take all of the time, and most of that time is dedicated to the rate, right? If I scroll up a little bit, I'll come back down to this in a moment, but if I scroll up, look at this chunk of paper starting from about here all the way up to about here is rate law, right? And then the other two terms, the inlet and the outlet, took like one line. And that's not at all unusual. The majority of the time we're spending on expressing R or R sub A in terms of whatever it is that we need it to be. So there's temperature adjustments, there's equilibrium constant calculations, there's relying on the stoichiometric table to express one output in terms of the other output, or sorry, 1 mole instead of the other moles. Very common, and that tends to be where the majority of the time gets spent, is figuring that kind of stuff out. So don't expect it to be short, right? Even for a problem like this, where the only thing I could argue about this problem is it's straightforward in the sense that all of the necessary information was there. We didn't have to go like search around a lot for anything that we haven't seen before, but that doesn't mean that it's easy or fast, right? It's definitely tricky. There are lots of places where mistakes can be made. So what I'm trying to do here is kind of show you what the usual cranking of the wheel looks like, right? In most cases, as you go through one of these problems, what does the solution procedure generally look like? And they generally follow something like what we had up there. It may not be N sub A that was missing. Maybe the temperature wasn't known, right? And so we couldn't evaluate any of those in terms of temperature or as numbers. We would have to leave some of those as functions of temperature and then solve for the temperature, which is usually a pain in the neck, but that's how it can go. So the second part of this question, we got about 15 minutes, which I think we'll be in good shape because we can finish up the second part. We'll come back and do the third part at the beginning of the next lecture, and then we'll move on to the energy balance. Were we given the V? Yeah, that one was given. So that was given right up here as 0.2 cubic meters. If you weren't given the V for this problem, you need to be given the V or more information, because you wouldn't have enough information to solve that one. So in part 2, there was this key phrase, which is 90% of equilibrium conversion. So the question was asking, what's the volume for 90% of the equilibrium conversion? Remember from our discussion of equilibrium, it sets kind of the high bound, right? No matter how fast the rate goes or how big the reactor is or what fancy chemicals or what fancy catalysts we use inside, we can never do better than equilibrium. There are some times where it might seem like we're doing better than that. We're going to show a tricky way to make it seem like we're doing better than that later, but we can never do better than equilibrium. And so this sort of a phrasing here, 90% of the equilibrium conversion, is a special type of process specification that pops up because it's saying, what if we wanted to do about 90% of sort of the best we could possibly do for that reactor? And so what this means is we want you to calculate, or I mean, someone wants you to calculate what is V in order to get X sub A as being equal to 0.9 times X sub A EQ, where X sub A EQ is the same conversion which you would get for an equilibrium reactor. Right, so that's everything that we were doing in chapter 2. And so you start off by designing your system as though it were an equilibrium reactor, but that by itself doesn't tell you anything about how big it is, right? Because there's no rate information inside of the equilibrium reactor. And then you say, okay, if I want to design a real reactor to get about 90% of what I could possibly do in the best case scenario with an equilibrium reactor, how big does the resulting reactor have to be? And that's a useful number to have, right? It gives you an idea of what's possible, right? Do I need one the size of a microchip or the size of a football field or what? This one is also set up a little bit different because now we will essentially know what X sub A is, but we won't know what V is. And so we can kind of turn the whole procedure around from our previous part of this problem, and kind of solve it in the opposite direction, which is why I chose this as an example. And so let's do the very first part here, which is set up our equilibrium reactor. Right, so this will look like the stuff from chapter 2, which is also what we spent a lot of time doing in homework 1. And so we're going to end up with K sub A. That's the one that we just calculated, right? That one was already calculated as 3.67 at 90 degrees C. And this will be equal to the product of our activities raised to their stoichiometric coefficients. What's a little bit different here is that I believe all of the reactors in the homework were given as a gas phase, and we're in a liquid phase here. So this ends up looking like X sub B over X sub A. And the reason that I know that is going from here to here, the activity of I is equal to the mole fraction of I for liquids. I believe that was table, I know it was in 2. I think it was table 2.1, right, where I summarized all of the activities. Anybody correct me if you happen to have the book open for which one. Oh, it's 2.1? Cool, I guessed right. Thanks, John. I'm just going to assume that I knew that well. X sub B, the mole fraction of B, is equal to the moles of B divided by the total moles. And similarly, X sub A is moles of A divided by the total moles of A. So ever so nicely, our moles cancel out. And so we're end up with N sub B over N sub A, which we can eventually write as XA 1 minus XA. The XAs that we're calculating here are XAEQ. Right, remember I had mentioned briefly in one of our lectures that when we were just dealing with equilibrium reactors, we didn't really care to specify that this was XAEQ and not XA. The difference between the two is XAEQ is the one for the equilibrium reactor, and the plain old XA here is for the real reactor. Right, we drop the EQ superscript when we're dealing with a real reactor. The question, isn't that inverted? No, I think that's okay. I'll give you why did I answer that so easily other than I've already done it? I'll show you in a minute. The reason why I'm so confident with this, because we have another way to calculate this. So if we go through this information, what we would end up with is that XAEQ is equal to 0.786, which is 78.6%. How can I check that? Well, I could go into MATLAB, I guess, and do it that way. But because we're dealing with a real reactor here, we have a sneaky way of checking that. The sneaky way of checking that is, remember that let's actually change this to a different color so that you remember that it's sneaky. Sneaky check. If we are at equilibrium, then the net rate is equal to 0. So the net rate of A is equal to 0. Remember, it doesn't mean that forwards and reverse have stopped. It means that they're equal to each other, right? The rate at which we go forward is the same as the rate at which we go backwards, and therefore the net rate of that will be equal to 0. If the net rate is equal to 0, we can use that to calculate what the equilibrium composition would be. So if you recall from the previous problem, we had found that R sub A was equal to 0.0139 minus 0.0076 N sub A. If we are at equilibrium, then this has to be equal to 0. That's the sneaky part, right? It's a sneaky way of checking whether or not you did your equilibrium reactor correctly. But it only works if you already have the rate law written, right? If you don't have the rate law written, then it's not that much help. So that's partly why I say that it's sneaky. So if you set that equal to 0, there's only one unknown in there, which is N sub A, and you have to end up getting the same result if you calculate the corresponding conversion, because you're defining equilibrium in two equivalent ways, right? You can either use the same approach that we did in chapter 2, or in these sneaky little check opportunities that don't come up all of the time, they just happen to come up. You can set the rate law to be equal to 0 and end up with a similar check. If you set the rate law equal to 0 without having actually done all the numerical substitutions that we did, you'll just end up with this equation again, right? It simplifies right back down to what we would expect, which is good because we expect to get exactly the same answer. So we can calculate another XAEQ, again, strictly as a sneaky check. You don't have to do this as part of the solution procedure. But if you do something like this, you end up with 78 point, I think I ended up with 78.5%, which is, it was rounding errors that resulted in the difference. So these two are equal to each other because they are equivalent definitions of the same thing, right? At equilibrium, both the net rate is equal to 0 and K sub A is equal to pi A, or the product of A. Both of those have to be the same. So this set are equivalent statements of equilibrium. It's one of those ways that you can help yourself to check the rate law whenever you write it on a complicated problem. If you already know the equilibrium conversion, you can check your rate law and see if you actually get the equilibrium from it or not. If you get the same thing, or as this case demonstrates, really, really close to the same thing, to within an approximate version, that's fine. Can I explain this part? Sure. The reason that that is equal to the way that I wrote it is that n sub b is equal to n sub a 0 times XAEQ, and n sub a is equal to n sub a 0 times 1 minus XAEQ. Right, so the n sub a zeros will cancel out, and I'll just be left with x over 1 minus x. The n sub t's have already canceled out. So if we know our x sub a, no, if you invert that, you'll get a different result. Our x sub a by our process specification is 90% of our equilibrium conversion. 0.9 times 0.78, we'll say 6 as the first one. So this ends up being 0.707, which is 70.7%. Right, so this now becomes the number that we put back into our problem. So from this sort of information, we now say, okay, if we needed 70.7%, then our n sub a is equal to NA0 times 1 minus XA, which will be 2.49, which is different from what we had before, right? But what's different about this one versus the previous one is we don't know what the volume is, right? We're trying to calculate the volume. So it's okay that we're getting different answers here because we're trying to calculate a new volume. Then if we substitute this back into our material balance, we have n sub a minus n sub a 0 minus r sub a v. We would go through the entire procedure all over again, right? The only difference is now we know what n sub a is. And so life would actually be a little bit easier because we know n sub a and we know n sub a 0 and all of our rate stuff, right? So we know this one, we know this one. We can plug in a bunch of stuff for r sub a. We already have an expression for r sub a. And so all we're left with is an unknown for v. So this would end up looking like 2.49 minus 8.5. The 2.49 comes because we're at 90% of equilibrium conversion. The 8.5 is the same feed that we saw before. And then we subtract off our rate, which is 0.139 minus 0.076 times n sub a. And n sub a here is 2.49. Right? Remember in the previous example, we didn't know that there was 2.49, but we knew v. Here, though, we know it's 2.49, but we don't know v. And so we rearrange this and we say that v is therefore equal to 1,186 liters, which is 1.19 cubic meters. And not surprisingly, that's kind of big compared to the other one, right? This one is about 6 times larger than if we were to run it the other way, right? If we run it at a standard 0.2 cubic meters, we don't get anywhere near the conversion, but the reactor is physically smaller. If you're trying to envision what 1.19 cubic meters looks like, and this is part of what you have to do on your homework, is try to come up with a comparison of that to an everyday object. That's close to the size of a car, because right, a car is on the order of about a meter wide and maybe 2 meters long and about a half a meter tall. You're somewhere on the order of about a cubic meter inside of there. Maybe half a car, something like that. But that's actually not that big for a reactor. I mean, we can very easily make these things the size of entire rooms or something like that. How come we don't get a different expression of R when the reactor is not at equilibrium? So it's the same expression of R. The difference is what's the value of N sub A we put in here. And so that has to work out just right. We're not actually at equilibrium, right? We're at 90% of equilibrium. There's an interesting thing you can try here. We're due for fika, so I'm going to take a few minutes. Try plugging in the number of moles if you are at equilibrium and find out what the required volume is. You will get an interesting number. If you go back up and change these numbers and say, well, what if I was actually operating at 78.6%? You'll get an unusual number for V. If you try to actually operate at equilibrium. Yes, and I'm going to the person who just said that in chat. Yes, it would be that, but I'm not going to tell everybody else. So yeah, 251. I have some tea over behind us, and we're about halfway through, and I don't want to keep talking for 2 hours because that's too much. I'm going to turn our waiting room music back on. Let's go ahead and show the sound here. Feel free to shoot me a question in chat. Get up, stretch, grab something to drink. I've got some peppermint tea that I'm going to have. And we'll come back a little bit after, right? Let's say, since we're starting a little bit late, we'll start the next one at 3:05. Right, because our fika is about 5 minutes late. So we'll start the next one at 3:05. So I'm going to mute my mic, but if you have questions, shoot them into the chat, and otherwise I'll turn on some music. Oh yeah, John asked if I can open up chat during fika. Definitely, it's open. Just give me a no in chat if the music's too loud, and I'll turn it down when I get back. Xantha, the question that you've got in chat there, doubling the initial temperature changes anything that's a function of temperature in equation 4.1, which is usually the rate constant and the equilibrium constant. I think for that particular problem, it was irreversible, so it would only adjust the little k, the rate constant k. The lectures are all lumped together, so if you want to get the recorded one, it'll be up shortly after the second lecture. Gonna get started in about a minute here. All right, let's get back to it. Turn off that's Scheming Weasel, if you're curious where that is. One of my favorites, not just because of the name either. It's nice. It's nice. It's 3:05, I'm about halfway through the peppermint tea. I'll probably keep working on it as we go. But we had said that the last thing that we were going to do with this example, we've got this all sort of worked out. Actually, let me save that. Make sure I don't lose it. The very last thing that we were going to do is try and solve the same problem that we had in part one, except we're going to try to do it in MATLAB. Again, we should come up with exactly the same answer, but I'm going to set it up a little bit differently so that you can see just a different way to go about solving this. So maybe that'll help sort of clarify in your mind what the different approaches mean, because they have to come to the same result, but also because this particular approach is really useful if you have more than one reaction. Excuse me. So if you have more than one reaction, you're kind of not ever going to be able to solve it by hand. You're pretty much stuck using a solver to solve it. It's sort of like the homework problem where you had two equilibrium reactions taking place in one reactor. There's not really a way to solve that by hand unless you just kind of get lucky with the algebra. Or you feel like if you looked at the solution, you can write up like the solution for a third order polynomial and it's disgustingly long. It's usually just easier to put it into MATLAB because you're going to end up having to put it into MATLAB anyway. So let's see how you could go about solving the first problem here. Oops, that was supposed to be my highlighter. Undo. Thank you. Let's solve this one, the conversion of A under the normal circumstances with the 200-liter reactor, but let's do it in MATLAB. We're going to take the same general approach, right? The general approach is we want to be able to solve the material balance, and we're going to try to solve it for n sub A. So when I'm first sitting down and getting ready to write up a problem in MATLAB, what I want to ask myself is, what's the variable I want to solve for? Because that's going to be the input variable to fsolve, right? And so I'm going to have to write everything in terms of that variable so that when that variable is guessed correctly, and MATLAB is the thing doing the guessing, the result is that the material balance is equal to 0. And so we've already written this in terms of n sub A, so we're going to leave it in n sub A because that way we don't have to change too much from our existing solution. So let's switch over to MATLAB here. And so the first thing I can do when I set this up is say, well, what do I want to solve for? I need to solve for my outlet molar flow rates. I'm going to opt to solve for both of them rather than just n sub A for a reason that I will show you momentarily in the script. So if I wanted to solve for both of them, that's two unknowns, right? It's n sub A and n sub B. You can set the whole thing up with just n sub A if you want to, and I will show you how you can do that when we get there. The first thing that the solver needs is always a guess, right? If you have no idea where to start guessing, pick the inlet conditions, right? So initially I know that there is no A, or sorry, 8.5 moles per minute of A. and no B, right? So I'll just guess that it's going to be something like that. And then I know what MATLAB is going to have to do is say, give me fsolve and solve the function I have to write. I still haven't done it, starting from my initial guess. And then once I have that initial guess, I'll then be able to go back and calculate my conversion. So this is where I would get started. I would start off with something like this. Now, the harder part becomes, well, how do I fill in all that stuff within the function? The way that I usually suggest that you do it is start working backwards. And so we know where we have to get eventually is that the material balances have to be set equal to 0, right? When n is guessed, where n is n sub a and n sub b combined into a vector, when those are guessed correctly, then the material balances must be true. And so the material balance on A, which I'll just abbreviate as MB sub A, that means the material balance on A. I know that has to be equal to NA minus NA0 minus RA times V, right? This is the material balance on A, and it has units of moles per minute. Similarly, the material balance on B is NB minus NB0 minus RB times V. This is the material balance on B, and this is moles per minute. So why did I write it that way? I wrote it that way because I don't have to think very hard about whether or not that's right, and I don't have to try to troubleshoot that very much in order to figure out that it's right. I can take that one simple small equation and go look at equation 4.1 and verify that I've written it correctly. Those have to be equal to 0 when the problem is solved, and the syntax for that is that these have to become the outlet, or the output variables. So the output here would look like this. So this should be equal to 0, 0 when solved, right? I haven't solved it yet. That's what fsolve is trying to do. I just know that those numbers will end up being 0 once the thing is solved. And so now I can go through sort of working backwards and say, I know by the time that I get to lines 7, 8, and 9, I have to have all of those parameters defined. If I don't have them defined, then MATLAB will give me an error and say, you don't have enough defined. So usually the first things that I will do is note that the inputs are arranged sequentially, but only because that's the way that I happen to do them. If this doesn't look familiar, see chapter 1, I believe it's section 8. But we're using the same syntax here that we used for the equilibrium reactors. It's just we don't have to always solve for X's or extensive reactions. We can always solve for the molar flow rates directly. And so what I mentioned a minute ago about writing it this way and working backwards, MATLAB's error checking machinery can be very helpful for us, right? Because we can just kind of say, like, I think I've written it up correctly. Let's see if I've got enough. So if I save this and I run it, right? So I'm going to hit F5 on my keyboard to run this. I'm expecting an error. Right, so I run this and I look through my error here and I go up to the top one. It says unrecognized function or variable n sub a 0. MATLAB has just kind of caught a mistake for me. It said you're trying to evaluate this, but I don't know what n sub a 0 is. So, okay, let's define n sub a 0, right? N sub a 0, we know previously was 8.5 moles per minute. If we take the sort of naive approach and say, I think that was the only error, let's run it again. Oh, we got another error, and it says, I don't know what R sub A is. So I'm going to go back into my code and say, okay, R sub A, I know is going to be equal to -1 times R. I happen to know that I'm going to need an R sub B. And then I know that R is going to be equal to K times a quantity of Ca minus Cb divided by Kc. Right, so the pattern that I want you to notice when I'm coding something like this is I'm not actually substituting all of those variables into the respective equations. I'm trying to keep them in their general forms. And the reason for that is because it's easier to troubleshoot these, right? It's easier to know if I left off the -1 in the wrong spot rather than try to use the -1 here and then keep track of the negative sign down here and any other negative signs that might be floating around, I'm trying to keep these expressions as close to the way that they're written mathematically in their general form, so that I have a better chance of tracking down my mistakes. So I'm going to continue to work backwards and say, I know I need to know these particular values. My n sub b0 is 0, because that wasn't involved. We did calculate a few things previously that we'll get to in a minute that are helpful here that we could have calculated inside of here but chose not to. We know from the problem statement that there were 200 liters for our reactor, and we know that the inlet volumetric flow rate was 1 liter per minute. Then we did some calculations in the previous problem that I'm just going to hijack here and put in there, but we could always do these calculations here. And so we know that K was 0.006, and that was 1 per minute. That was the adjusted value at 90 degrees C. So it was 0.06 at 60 degrees C with units of per hour, and then we adjust for temperature in units and get 0.06. Similarly, our KC was 3.67, and this was at 90 degrees C as well. So maybe I think at this point, like, wow, I've typed a lot of stuff. I think I've got it all in there. Let's try and run this again and see if I've got everything. If I run it again and I check my errors, I can see that, nope, I just forgot one, right? Unrecognized function CA. And so because I've been writing this in a fairly general way, I can continue to use fairly general definitions here and say, if I know, or if I need to know what CA is, I know that CA is defined as NA divided by V0, right? And this will have units of moles per liter. And I know that CB is NB divided by V0, mole per liter. And so that makes this rate expression easier, right? I don't have to substitute in all of these stoichiometric expressions or anything like that. I know it's all getting handled inside of there because I've been writing it in the most general way that I can. So I think I've solved this again. Let's go ahead and try running it again and see what we get. It's at least converged. Let's take a look at the output value. So if I just check nsol, I see that n sub A is 4.46, and I see that n sub B is 4.03, maybe 4.04, kind of depends on how you would like to round those. And those are identical to what we would have seen previously. So I can calculate conversion as 1 minus n of 1 divided by 8.5. Oops. Nsol of 1. Right, and I end up with 47.5%, which is pretty much the same as what we got before, right? We got a little bit less than 45% last time. The difference typically is when I'm writing those numbers out, I'm rounding them to, 2 decimals or something like that. Whereas MATLAB is keeping them out to, I think the float syntax is like 16 decimal points or something like that. But we've got essentially the same number except for rounding errors. And so this sort of a structure on your root finding function here, where I start off with the most general expression, right? I know that that's always going to be true, and I don't have to worry about a lot of checking the terms on each one of those, because I can go look at the book at equation 4.1 and notice that it is almost identical, right? It's very easy for me to say, oh, okay, I couldn't actually write the subscript. I just wrote NA, and that's N sub A in equation 4.1. Similarly, I wrote NA0, and that is N sub A0 over in the book. And so this sort of a syntax is very convenient. If MATLAB's giving you an error thinking that MB and MA are variables, they should be variables. They are. I've defined them to be variables in the way that I've got them here. Potentially your error could be that they're not used the same here. Is there a reason I didn't include calculating XA in the script? Yes, because I wanted to make it actually easier in the sense that I don't actually need conversion because I have asked MATLAB to solve for both of the molar flow rates simultaneously. And so if I essentially have access to those, right? I'm guessing those values until the material balances are solved. Then the code that I need underneath that is much more simplified. And so I'm actually glad that somebody asked that in the chat, because if you wanted to solve it just for n sub a, then you would need that additional information. So for example, if you wanted to change this, right, and just solve for a, then that means that this n sub b is no longer valid, and you would now need to calculate n sub b as equal to n sub a0 minus na, right? And so I don't need that particular calculation if I do it the other way around. I also don't need the x sub a anywhere in there. It's kind of implied in that particular writing, but I don't need it anywhere. If this can't be written or is not immediately obvious to you, that's okay. You can use the other form that I had a moment ago, and you'll get the same answer both ways. But that's the reason that I wrote it the way that I did, was just in case this is not easy to write, and sometimes it's not. This is the same syntax that I have in a different problem in the book. So one thing that you might want to see is example 4.7. See also example 4.7 for multi-reactions that look like this. Right, so what you'll notice there is the only thing that will change significantly between the code as I've just written here for one reaction and the code as you would need it for multiple reactions is very, very little. The only things that change are the rate expressions down here, right? So instead of just R sub A being equal to one of the rates, you would add them up for multiple rates. And that's another advantage of writing the code in this way, sort of backwards to forwards from bottom to top, leaving these general expressions in there is it's easy to expand them to more complicated problems, and it's easier to see where those changes have to be made because you don't have a bunch of sort of mysterious numbers floating around. Personally, I would not like to write the K this way, just because, well, what if I made a mistake with K, right? It's hard for me to know if there was a mistake in K if I just write it as 0.06, if it's not being calculated inside the script. Now I have to go get my pencil and paper and manually check K every time I want to check K. But I did it here because time is of the interest right now. So we happen to have it already calculated for the previous problem. So we kept it here. So any of these problems that you can solve by hand, you can also solve in MATLAB. The reverse is not always true, that anything you can solve in MATLAB can also be solved by hand. And I think you may have gotten a feel for that in the first homework, where some of them it's like, yeah, I can approach this by hand, right? This is possible. But then as the complexity goes up, hand calculations just kind of go out the window. Nevertheless, the approach is very similar, right? It's just in these scripts, I like to work backwards, right? When I write the material balance here, the next thing that I write are the net rates. Whereas, you know, in MATLAB, that's working from bottom to top. If I was doing this by hand, as we just saw in the previous lecture, that's going from top to bottom. That's only a quirk of the syntax, right? Our brains work from top to bottom when we're writing things out. MATLAB code requires us to have those values evaluated already, but we can just switch it and go from bottom to top. So I will post this code as well, so that you've got it as another example that you can try and compare to either your handwork or any of the work that you would need for the homework problems. You can use code very, very similar to this for the first few homework problems. In fact, for nearly all of them. As the complications go up, if you get to a multi-reaction problem, that example of code is in 4.7. And so that's basically writing exactly what we've got here and just using net rates instead of rates, instead of individual rates, which is great because the changes there are fairly minimal. So again, I will post that, but I am going to actually, I'll give it a moment while I pull up a different screen, but then I'm going to go back to my notes here in a moment. Okay, back to our notes here. Let's introduce the energy balance. So what I want to, the emphasis that I want you to have here with the energy balance is how is it similar to what we've already seen in, actually you would have seen the energy balance in both thermo and 100. The energy balance that we use here frequently looks different, right? It looks like something that we haven't seen before. And so all I want to do is reassure you that it's exactly the same thing. The translation from what we've seen in previous courses to what we've got here is about a 3 or 4 page derivation that's in your book. So you're more than welcome to go through that. If you take my word for it that I did the math right, and that's an important one. I checked that one a few times, although I could have a typo in there. I'm pretty sure that the math is right. The general approach is the part that I want you to be aware of and what each of those terms mean, because that'll help you when it comes time to analyze problems. So generally speaking, the energy balance that we have seen previously usually simplified down to what we call an enthalpy balance. So we didn't often work in internal energy and flow systems because most of the time in flow systems, it was more convenient to define this parameter of enthalpy as U plus PV, which should look pretty similar to what you would have seen in thermo as well as 100. And it just so happens that that PV term popped up all over the place. So it was convenient to define enthalpy that way. And so the energy balance, what it used to look like in previous courses, which was a very general form, and it's very general, which means it works all the time, was that the total enthalpy of something going out, N sub I, H sub I, summed over all of the components from A to Z, minus the total enthalpy coming in, N sub I 0, H sub I 0 from A to Z, was always equal to Q plus W. And specifically, it was equal to shaft work. It was never equal to PV work because the PV work is embedded inside of the enthalpy. And so what this meant was that we could usually get away with writing like a super stoichiometric table, or anybody have Dr. Opakowitz for 100 or thermo, because I think he calls it a magic table, which I wholeheartedly support. I need to get into the habit of calling it a magic table because that is some magical stuff. Oh, it's a table of wonder. That's all. Who called it the table of wonder? Was that Dr. O that called it the table of wonder, or somebody else? Dr. Chen? That's so great. Yes, table of wonder. I think mine is fairly dry. I just call it a stoichiometric table. The reason that I call it a stoichiometric table is because you don't need to know anything other than stoichiometry to do it. It's to contrast it from a rate law. Yeah, I dig the table of wonder. I might do that again. So the table of wonder for these types of problems was you would have some moles going in. It would be at some initial temperature, actually not even temperature. They would just be coming in at some initial enthalpy, and then they would be coming out at some flow rate with some exiting enthalpy. And the way these tables of wonders were set up would be you'd have your stoichiometric coefficients, and then you would have N sub I 0 and H sub I 0. And then you'd have your N sub I here and your H sub I over here, right? And you would frequently have, let's say, A, B, C, D through here. And then you'd fill in the numbers all the way along there. And every once in a while, you would be able to say, like, I'm just going to randomly set this one equal to 0 because that happened to be our reference condition, right? I hope that is bringing back, I'm going to call them good memories. And then we would do things like, okay, the amount coming out here was the in plus the stoichiometric coefficient times squiggle, right? And we'd set up these big old problems and solve them that way. I am pointing this out to say this still works. You can't break the first law as long as you do it correctly. That still works. The reason that we're not going to use that particular approach is because we're only ever going to look at 3 material balances. And for this particular reactor, we only need 1, right? We need one energy balance per reactor. So it still works, we just write it differently. And the reasons that we write it differently is because we keep encountering the same conditions over and over and over and over again. And so we don't have to start from this super general although magical and wondrous table every single time we want to solve this, right? We can take some shortcuts and say, I know these terms always look similar. And in fact, I know that they have to have something to do with the rate of reaction. And that's not immediately evident from this particular table. So the end result of where we get to is equation 4.2 in your book. And so I want to write that out once so that we can talk about what the various terms mean. So that exact same concept applied to a CSTR gives us equation 4.2, which is our energy balance. And so equation 4.2, first of all, we write it in root finding form because there are like almost zero times where we will ever solve this in anything other than MATLAB. And it's not like, oh, MATLAB's amazing. It's just, you generally can't solve these things by hand. There are a couple of situations where you can, like on some of your homework problems. But the reason that it's set up this way is with anticipation of trying to give it to a numerical solver. Whether you give that to Python or MATLAB or Mathematica or whatever, they all have to have this kind of a form. It just so happens that we use MATLAB for it. So it has essentially three components to it. So the first is the sum of ni0 c sub pi t minus t0. This is summed up over all species. Plus, I'm going to simplify this part a little bit. We'll come back to it in a moment. Plus r times delta h times v minus q minus work shaft. So let's look at each of these individually, and then we'll modify them a little bit. This particular term here, the first one that we've got, the interpretation of that is there's some stuff coming in. It initially came in at some temperature T0. It's coming out at some temperature here. This C sub P is, remember, our proportionality factor. It says if I have a certain number of moles of a component and I want to heat it up to a particular temperature, so apply some kind of a temperature difference to it, how much energy do I need? And so also notice that the only one that's being counted here is the inlet moles. And so what this term means conceptually is this is the amount of E, energy, to heat the inlet species up to the reactor temperature. There are some assumptions that are put inside of here, and they are assumptions that will hold everywhere through this class. And if they don't hold, you're not stuck, right? We haven't taught you what to do if they don't hold. But if they don't hold, you have to go back to the table of wonder, because the table of wonder is the most general possible approach that you can get. We have some specific requirements that work for a large number of reactors, and so we assume that they're always true. So the assumptions here is that phase in is equal to phase out. So if you feed component A as a liquid, component A has to come out the other side as a liquid. If you feed component B as a gas, then component B has to come out as a gas. It is okay if A and B are in different phases. That's not a problem, right? We occasionally will use this to feed liquid in, and then we will produce a liquid stream and a gas stream. That's okay. But we can't have a phase change of a single species from the inlet to the outlet. So if A comes in as a gas, it comes out as a gas. If it goes in as a liquid, it comes out as a liquid. But the different species can be in different phases. The other major assumption that we have is that C sub P is constant. So if you need a heat capacity, go see Appendix D. And I've tabulated a bunch of heat capacities for you. Heat capacity can be a very strong function of temperature sometimes. And so I've tabulated the heat capacities at four different values of temperature. And so just find the temperature that you think is most representative of your reactor, pick that heat capacity and use that one. you will get slightly different answers from your friends or even potentially from me if the temperature of your reactor is not explicitly listed as one of the 4 that I've got there. That's okay. Don't worry about that. What you'll see is that if you're fairly close, right, if you're like 200K this way or 200K that way, the heat capacity differences are pretty small. And in fact, in some of the species, the like gases and stuff like that, you can change by 400, 500, 600K and the heat capacity barely budges. But the heat capacity is always constant. So just pick the one from Appendix D that you think is best for your reactor, best for your temperature, and use that one. By the way, the derivation for that, like if you want to see, well, exactly why is it assuming those lets us produce the form that I've got there, it's all in your book. Every step of that is worked out, but I don't want to spend 45 minutes doing algebra. I already did it once, right? It's not like CENG 100 where I need to show you the algebra because it'll be different every time. It's always this. It always looks the same. This term over here, if we just look at the units on here, it can be a helpful thing to remind us what's happening. So the rate term here usually has units of moles per volume per time. The enthalpy looks like energy per mole, and the volume just looks like volume, right? That's not surprising. If you lump all of those together, what you're saying is if I am producing things at a particular rate of moles per volume per time, and I use basically a unit conversion that says for every mole that I produce, I have a corresponding amount of energy, and that's our enthalpy of reaction, and I multiply that by how much stuff that I have, that's got to give me my energy production per unit time. And that's exactly what's being described here, is if this reaction is occurring at a particular rate, and every time that reaction occurs, it gives a particular amount of energy, and I know I'm doing it in a particular volume, here's how much energy has to be coming out. And that's exactly what that term means. So this term means energy generated, I'm going to say generated or consumed by the reaction. We're being a little bit sloppy there with our definition of generate and consume, right? Energy is always conserved. And so when we say energy is generated or consumed, we just mean that it's moving from like the internal vibrations of a molecule, the stuff that was internal energy previously, to something we can measure, which is temperature, which is usually kinetic energy of stuff. So energy released by the reaction, absorbed by the reaction. The sign will depend on whether it's an endothermic or exothermic reaction. The enthalpy term that we have here is our enthalpy of reaction. It's the same enthalpy of reaction that we were using for our equilibrium discussion. And if you play some of the same tricks, what you can get is that the enthalpy of reaction can be adjusted from any reference enthalpy of reaction by an expression that looks like this. I should get a third color on here. So the little r's here, so this is our reference enthalpy. This is our reference temperature. So that's the temperature at which the reference enthalpy was calculated. This is enthalpy of reaction, not or, of reaction. This was actually of reaction too. At the reactor temperature, right? Because we've got the little t over here. This is our reactor temperature. The reference enthalpy here, it can be calculated in exactly the same way that we've calculated our enthalpy changes previously. Oops, no, I want those, but then I want to delete them. There we go. We just use a different word for it, but it's exactly the same thing. This can be calculated as the sum of the stoichiometric coefficients times the enthalpies of formation at their reference states. All right, so that's the same thing that we've seen before. The delta CP is a little bit new, but it's, hey, that's a good pun. It's new, but it depends on new. God, I love it. what's the terminology? I think the hip word for that when you make a pun like that, I yeeted it. Y-E-E-T. I yeeted this thing. C sub P, comma I. Right, so if we sum up the stoichiometric coefficients times their heat capacities, I'm teasing you, I know what yeet means. It means you did something badly. This delta symbol here, let's switch back over to our colors. Anytime we need to calculate a delta in this class, it was actually already defined previously in our thermo chapter, so you can review the thermo chapter if this looks weird to you. Any delta of any quantity m is always the sum of the stoichiometric coefficients times m sub I. So they're kind of new, but they're exactly the same forms that we've seen in chapter 2. It's just we may not have needed them. Right, so that's how we can adjust our enthalpy of reaction. The reason, by the way, how come we introduced it new, right? How come I, see, new again, you did it again. How come I called it delta HR instead of some other kind of delta H that we've seen before? Only because occasionally we're just given that value. So occasionally we do not have to use this particular form, right? If I just give you a reaction like A goes to B or something like that, I might just tell you that delta H is equal to some value at some temperature, and that's supposed to indicate a reference one, something like that. You're ruining this for me in chat. I'm trolling you. I know what that means, but thank you. I'm glad that it has. I wish I could see you because it's one of my favorite parts of teaching is making bad puns and watching people wince about it. And now it's like, yeah, I can't see you. These particular terms over here are energy being transferred through the walls, specifically through the control volume. Is delta CP basically C sub P mix? No, that's a good question. So C sub B mix that you're used to in thermo is not delta CP. So that's, thank you for pointing that out. I always forget about CP mix because I don't teach thermo a lot. The CP mix, if you ever wanted to estimate the heat capacity of a mixture, was defined as the mole fractions times C sub Pi. That's very different from summing up the stoichiometric coefficients times C sub Pi. So it's very easy to get delta Cp equals 0 and something like that. Oh, good. I'm glad so many people are grimacing in chat. I love it. So thank you for asking that. No, delta Cp is not the same as Cp mix. Frequently, delta Cp will be 0 or very close to 0. One of the great things that we're going to do in this class for our CSTRs, never worry about shaft work. Shaft work can be important because occasionally the power of that motor can be on the same scale as the rate at which energy is being produced by the reaction. So if it's not being produced very quickly, or if the mixer is quite intense, so you've got, you know, a 30 horsepower mixer or something like that on there, then occasionally the shaft work can be important. It can also be important if your materials are very viscous, right? If it requires a lot of motion to shear those, or a lot of energy to shear those two layers next to each other, like you would have in a polymer, then the shaft work can be important. But for us, it's never going to be important. There will never come a time where that shaft work is relevant. If you ever need it in the future, frequently it just looks like take the power of the motor and put it in there, right? If it's a 1 horsepower motor, convert horsepower to joules per second or whatever you need it to, and use it that way. So you can do it if you need to later, but nowhere in this book are we ever going to worry about shaft work, because it is usually like a pittance compared to the rest of the energy terms that are involved here. Oh, I missed one thing. If you ever need to extend to multiple reactions, that will look like plus V times the sum of all of the reactions times their corresponding enthalpies. And so the extension of the energy balance from one reaction to multiple reactions isn't too much, right? In a single reaction, you've got just a 1R delta H term, right? There's only one reaction, so there's only one R. There's only one delta H, so there's only one delta H. If you have more than one reaction, then you just sum up all of those terms. The R that sits in there is exactly the same R that we've been dealing with before, right? It's your rate term. In fact, there are very few new terms that we've got in here. We've somewhat modified the enthalpy term here, right? We've made that look ever so slightly different from what it was before, but conceptually it's the same thing, right? It's an enthalpy of reaction. And a heat capacity is new, right? That wasn't in our material balance, but I know you got heat capacities down. And then we canceled out the shaft work, so we don't have to worry about that one. The only one that could truly be like just brand new, never heard it in thermo, never heard it in reaction or in material and energy balances, is the Q term. And so the Q term is how much energy can we lose by a thermal gradient or gain by a thermal gradient, and that comes from a heat exchanger. And so if you think way back to our initial, yes, you just assume work shaft is negligible. So every time you write that energy balance, just drop the work shaft. You never need it. If you think back to the way that I first sketched the CSTR, I would have sketched it something like this, right? And I had distinguished between our process fluid, which was in here, which would then, come out somehow. So this was our process. And then I had also said that there is a utility, right? And so the utility would come in here and it'd go out here. What that utility is doing is interacting with the walls of the reactor and exchanging energy with it. And so we call this a heat exchanger. I'm going to write this up here. That term is probably familiar from at least 100 because you probably did the magic table or the table of wonder for a heat exchanger. And so the way a heat exchanger works is if this is hot and this is cold, the energy goes from hot to cold. It's still that, right? We can't break that. It's still exactly that. What's different though is the way in which we relate the energy, because we don't want to have to write too many different variables. We want to keep the same energy variables in each expression, right? We don't want to have multiple Qs floating around or something like that. So for more details on the heat exchanger, these are in section 4.3, but the main idea of a heat exchanger is that there's only one term for it, and that is Q. It's not one term, sorry, one expression. Q is equal to U times A times the temperature of that utility minus the temperature of the reactor. So this T is your reactor T. This T is your utility T. Right, so this would be, if you have to heat things up, we like to use steam. If you have to cool things down, maybe it's water. The A that's here, area available for heat transfer. And so you might, whenever you calculate A, you might have to do some geometry, right? If this is a cylindrical tank, and I know that this distance, the diameter here is D, and I happen to know that the height of the tank from here to here is H, the area available for heat transfer is everywhere where you've got process fluid on one side and utility fluid on the other side, right? So that version that I just got here, this area, is the area for which you've got utility on one side and process fluid on the other side. Sometimes it'll just be given to you. You'll just know A because it'll be given to you. But maybe sometimes we'll say, the diameter of the reactor is a meter and the height is 1.5, and it's sitting inside of here like this. Calculate the area, and you'll just honestly, I don't remember a lot of my geometry, so I end up Googling it. Thank you. It's U times A, so we've got one more term to get to. This Q, it's the same Q as in equation 4.2. So you don't, all of the sign conventions have already been applied for you. You don't have to switch it and say like, well, that's the Q for the heat exchanger, so it gets a negative or anything like that. All of that's been done for you, so it's the same Q. This U, and I've got 1 minute left, is called an overall heat transfer coefficient. The most important thing about U for this class is it's constant. So it's not going to be anything that we have to calculate in terms of like not knowing it ahead of time. In order to calculate it, there's a simple equation, which is 1 over U is approximately equal to 1 over H plus 1 over H sub U. And these values are all tabulated. So the H's that are here, these are individual heat transfer coefficients. Yeah, there was a comment, thank God we don't have to calculate U. Yes, we have an entire class dedicated to almost that, which is our heat transfer class. And then it can be a research project all on its own to figure out what these values are. But at any rate, all of these are tabulated, and there's only like 3 possibilities for those H's or 4 possibilities. So if you ever need to calculate this, just check your book for equation 4.28. It's like a 2-step calculation. You just look up the value of H, look up the other value of H, plug them into that expression, and you're done. You've got U. I do that because you can get a pretty good estimate of a lot of different things. And I would like you to know where that U comes from so that when you see it again in your heat transfer class, you say you have an example of why something like that would be useful. So don't stress over U. It's just go look at 428 because it's the only thing that you can use to calculate it in this class. And you just do a little 2-step calculation. So it's 3:51. I don't want to go over any more than this. Friday's lecture, John's going to look at some examples. Monday's lecture, we're going to look at examples all over again. So we're just going to be looking at this for the next couple of days. So thank you all. I hope everyone is staying safe, staying healthy, staying well. I'm going to go ahead and stop presenting anything new. But as always, I'll stick around for 5 or 10 minutes. I know John is in chat, so I'm going to unlock the chat so everybody can chat. Shoot me a question if you've got any. Otherwise, I will see you back here with John on Friday. And don't forget to keep working on homework too. See you, everybody, or everybody that's leaving. I'm going to pop our music on because as John pointed out, it is super awkward to sit here in silence and stare at a camera. Hold on. Let's try. I'm going to do 10 seconds of staring. Ready? It's going to be super awkward, I promise. Here we go. 2, 1. It's terrible, right? That was just 10 seconds. Can you? I know, right? It's terrible. It's absolutely terrible. So anyway, let's turn some music on because you can't just like stare at it. Can you scroll up to the H equation? Sure. Can you be a little more specific? Which H equation? This one? Yeah, sure. You can ask questions over the mic. Hang on, let me undo this so that you can ask questions. Okay, you should be able to unmute yourself.
Yeah, just like a general question about not the class specifically, but what got you into teaching and just having such a passion for it.
It kind of built up over time. So initially when I was doing my undergraduate, and yes, Max, I see your question in chat. I'll grab it in a minute here. I always really liked the sort of book stuff, right? The idea of you can write down a list of assumptions, and through the enormous efforts of us generally over the last like 100 or 200 years, right? I think a lot of times people kind of take this stuff for granted, but I mean, we didn't even know what the structure of the atom was back in like 100 years ago, something like that. We didn't even know the neutron was there. So it's just wonderful to me that we can start with assumptions, and we have these basic rules of the way that we know things have to work, and we can come up with a prediction of what's going to happen. And that was really interesting to me. And I worked for about a year for a polymer company, and it wasn't what I wanted, right? I wanted to really be involved in that sort of stuff. And so I looked around. It came as something of a shock to realize, like, yeah, you can actually get a job as a professor. Like, those people do that for a living. And so that pushed me to the PhD. And then the more I did it, the more I realized, like, I'm not really interested in writing up grant proposals and reading papers and writing papers and all that kind of stuff. I loved the research aspect of it, actually being in the lab and doing the experiments. I thought it was great. But I hated all the paperwork on the other side. And that paperwork, when you become a new faculty member, is intense. But I also had the option to be a TA multiple times. And that was what really sparked it, was my option as a TA a few times, was to realize that I like doing that. It's surprisingly difficult to sort of go through a lecture, because it's not just following your notes. You have to try to understand the material well enough that you can answer questions on it, and that's tough. It's one thing to be able to run the equation, but when you say, I need to actually learn this, it's a big motivator to actually read a textbook and figure out what the ideas are behind it. And then once you start to see all these different ideas, I couldn't just help but be passionate about, putting them all together, because it was so neat for me. And so eventually I found out that there are positions like this one where your primary responsibility is teaching. And so it was a slow progress over like 10 years of figuring that out.
Cool. Thank you.
You're welcome. Some hints on how we can approach problems 2 and 3. Let me pull those up real quick, just so I don't lead you astray. Let me make sure I'm not, okay. I don't want to share the solutions. So problems 2 and 3. Yeah, so problem 2, you're going to set that up close to the way that we did the previous example. And I say the previous example, not the one from today, but the one from Monday's lecture. And the reason that I say close to that one is because this is an irreversible reaction. And so your non-elementary rate law looks like this one. And so your rate law here is actually very much simplified compared to what it could be, because there's no dependence on the concentration of B. And so roughly what you're after is the same approach that we had in the Monday's lecture, where we express each of those in terms of either conversion, or if you wanted to do it the way we were doing it today, express them in terms of N sub A and calculate what's coming out the other side of your reactor. For problem 2.3, so the tricky part of problem 2.3 is not that the reaction has changed, it's that the reactor setup has changed. And so what I'm trying to do in problem 2.3 is remind you that this stuff all takes place in the general context of the same types of problems that we saw in CENG 100, or I suppose it could have come up in CENG 102. So what I mean there is, in problem 2.2, you're basically looking at one CSTR, right? In problem 2.3, you've still got one CSTR. It operates under all exactly the same conditions, except it's part of a larger process. And that larger process is one that even has a special name in some contexts, which is RSRP, which is you have a recycle. And so this was our separator. This was our reactor. And so what I'm trying to show you in that problem is the way that we used to have to solve this was the only option that we had was to try to use the squiggles, right? And we would set up a bunch of material balances and try to solve it that way. That's not how we normally do things because we don't know squiggles ahead of time, or we don't know enough about them enough about the rest of the system to get squiggle. And so instead, how do we solve this if we have to say that R is equal to K C sub A? And so the approach here would be very similar to what you had seen in 100. So you do a material balance around A here, do the same material balance on A that we did here, right? Except now your material balance here is equation 4.1, right? It's the material balance for a reactor rather than the material balance that we had seen previously. And then you do a material balance around the separator. It's not my intent to trick you with that specification there about removing 60% of the unreacted ethylene glycol. What that means is if there were 100 moles of A here, there would be 60 moles of A here and 40 moles of A here. And so one of the implications there is you can solve that problem just by tracking A. You don't really have to worry about B if you don't want to. But I'm not trying to trick you with that specification about the separation unit removing and recycling 60% of the unreacted ethylene glycol. It just means if there's 100 here, there's 60 coming out and going back to the beginning. And so now this term up here would be, you know, whatever, 60. And then I don't know if I gave you an inlet molar flow rate. I think you have to calculate that. It's 10 mole percent ethylene oxide, and it's coming in at 4 liters per second. So you'll need like a molar mass or something to take 10 mole percent and switch it over into a molar flow rate. So if there happen to be 5 moles coming in, which I'm just making these numbers up, so don't use them, then the feed to the reactor would be 65. And so it'll require you to set these up so that you can solve them. I guess efficiently would be the word, because the inlet to the reactor depends on the outlet of the reactor. And that's not anything new for us, right? Not for CENG 113. It's just a reminder that reactors do not operate in isolation. They're part of a bigger system. I put the 3 stars on there instead of 2, not because the reactor part is difficult, but it just may have been a while since you've done a calculation like that. But you should remember that it's there because that's how these things are really set up. It's never just dump raw materials into a reactor, get exactly the purified product that you want out, and ship it. It's always part of a bigger system. Yep, definitely, John. All right, we're a little bit past 4, so I'm gonna wrap things up. I'm gonna stop our recording too, and I will see everybody on Friday. Stay safe out there. John will make a breakout meeting for us. I just need to stop the recording.